Hey there and welcome. Today, we're going to pull back the curtain on the processor, the brain of your computer. We're going to figure out how it goes from a simple mouse click to literally billions of calculations in the blink of an eye. So let's dive right in. Seriously, have you ever just stopped and wondered what is actually going on in there? Every time you click or type or watch a video, billions of tiny operations are happening every single second. How is that even possible? Well, we're going to find out. Think of it like a construction project. We're going to assemble all the key building blocks, one by one. All right, so any good construction project needs a solid blueprint, right? Well, for pretty much every computer made today, that blueprint is something called the von Neumann model. It's this incredibly simple but really powerful design that basically started it all. What's so amazing is just how simple and elegant this blueprint is. John von Neumann proposed this way back in the 1940s, and it really boiled down to four key ideas. First, you've got a central brain, the CPU. Second, you have a memory that holds both the instructions for a task and the data needed for it. Third, that CPU can talk to that memory directly, no middleman. And finally, it just follows the list of instructions one after the other. That's it. This design is the absolute bedrock of all modern computing. Okay, with our blueprint in hand, let's start building our most important component, the brain itself. The central processing unit, or the CPU. You can think of it like a company headquarters, with a few really important departments that have to work together perfectly. So first up, we have the head office, the control unit, or CU for short. This is the manager of the entire operation. Now, it doesn't do the heavy lifting itself. Instead, its job is to read the to-do list, figure out what needs to happen, and then send out orders to all the other departments, telling them exactly what to do and when to do it. It's the ultimate coordinator. Next up is the department where the real work gets done, the arithmetic and logic unit, or the ALU. This thing is the powerhouse calculator of the CPU. Anytime the computer needs to add two numbers, or compare if one value is bigger than another, or do any kind of math or logic, the control unit sends the task right here. This is where all the number crunching happens. So the manager and the calculator, they need a place to work, don't they? And that's the Immediate Access Store, or IAS, which you probably know better as RAM. Just think of it as the main work desk sitting right next to the CPU. It holds all the programs and data that the CPU is actively using right now, because grabbing something from this desk is insanely fast compared to, say, walking all the way over to the main file cabinet, which would be your hard drive. But here's the thing. Even that work desk isn't quite fast enough for some jobs. Right inside the CPU itself are these tiny, unbelievably fast little storage spots called registers. So if RAM is the desk, registers are like little sticky notes that the CPU keeps right in its hand for the most critical, I need it this instant, information. And these sticky notes, well, they basically come in two flavors. On one side, you've got your general purpose registers. These are like blank sticky notes, where the CPU can just scribble down any piece of data it's working with at the moment. But on the other side, you've got special purpose registers. Think of these as pre-printed forms with specific boxes to fill in. Each one has a single, dedicated job that is absolutely vital to keeping the whole operation running smoothly. So let's meet this special team, shall we? The program counter, or PC, is the planner. It's always holding the address of the next thing to do. Then there's the memory address register, the MAR. That's the navigator. It holds the specific memory address the CPU needs to go to right now. The memory data register, or MDR, is kind of like a little loading bay, briefly holding data that's coming from or going to memory. And finally, the current instruction register, the CIR, holds the instruction that is being worked on at this exact moment. These four work together in this perfect little ballet to manage the flow of information. Okay, so we've built the headquarters, the workspace, and the notepads, but they're all pretty useless if they can't communicate, right? Well, they're all connected by a set of electrical pathways called system buses. Just think of these as the information highways that connect all the different parts of our little computer city. And here's how the traffic flows. The address bus is a one-way street, running from the CPU out to memory. It only carries the postal address of where information needs to go. The data bus, that's a two-way highway. The actual data and instructions travel back and forth on this one. And then you have the control bus. This is like the traffic light system, carrying all the timing and control signals from the control unit to make sure everything is synchronized and you don't get any digital traffic jams. All right, we have all the pieces. We have the highways connecting them. Now it's time to flip the switch and bring our machine to life. And to do that, we need to understand its fundamental operating rhythm, its constant ticking heartbeat. And that heartbeat is this, the fetch-execute cycle. It's a simple, repeating three-step dance. Step 1, fetch. The CPU looks at the program counter, goes to that address in memory, and grabs the next instruction. Step 2, decode. That instruction gets put in the current instruction register, and the control unit looks at it and figures out what it's supposed to do. And finally, step 3, execute. The control unit sends out all the necessary signals, and the instruction gets carried out. Fetch, decode, execute. Over and over and over again. And that's really the secret sauce. That simple three-step rhythm, that constant heartbeat of fetch, decode, execute, is repeated billions of times every single second inside that little chip. It's the engine that drives every single game you play, every website you browse, every line of code you write. The entire complex, beautiful digital world you see on your screen is all built on this one incredibly fast and relentlessly simple cycle. And now you know how a computer really thinks.